Okay, so good evening everyone. So we are back with the remaining topics which is left in this is coordination compound unit 9. Okay, unit 9. Okay, so we are doing lecture number 5. So today's topic is valence bond theory. Dear students, remember this valence bond theory is very important for your board examinations. Okay, every alternative years they are asking here questions for 2 or 3 marks. So VBT theory, based on VBT theory. So please try to understand it properly from the beginning so that you don't face any problems in your board examinations. Okay, so what is valence bond theory? Let us first try to understand. So in valence bond theory, what is it? The ligands donate electron pair for coordinate bond formations. In this valence bond theory, you will see that the ligands is there. Huh? So those ligands, it will be donating the electrons for the formation of what? The ligands donate the electron pair for coordinate bond formations. Okay, to whom? To the central metal atoms. Okay, for the here comma is there. So the ligands, they are going to donate the electrons to the for coordinate bond formations, and central metal atoms, okay, central metal make available required number of empty orbitals. So these central metal atoms, they make the available required number of empty orbitals. Okay, so central metal atoms, they are making it available. What available? They are making it available the number of empty orbitals. Okay, which will be required for formation of bond to produce a coordinate bonds. Okay, so what is, according to valence bond theory, the ligands donate the pair of electrons to the central metal atom for the formation of coordination bond. Central metal atoms make available the number of empty orbitals, okay, to produce a coordinate bonds. Okay, so this one you have to keep it in mind. This is also called as VBT theory. Now in VBT theory, there are few things which you should know before we start. Okay, so hybridization, when you will get a hybridization D2sp3 or sp3d2, then what will be the structure, what will be the shape of that particular compound's coordinate compound? That will be octahedral, okay, geometry. If the hybridizations you are getting is sp3, then the geometrical structure here, it will be how much? What will be the geometrical structure here? Tetrahedral. And if you are getting the hybridization dsp2, then the geometrical structure will be square planar. Remember this, students. Now stereochemical series, okay, spectrochemical series. So in a spectrochemical series, what we are going to discuss is, here we are going to discuss about strong field ligands and weak field ligands. So these are the weak field ligands: I negative, Br negative, Cl negative, F negative, OH negative, H2O. Okay, there is no negative. So these are the weak field ligands, okay or not? And these are strong field ligands: NH3, En, NO2, Cn, CO. So these are strong field ligands. This one you have to remember it, okay? Spectrochemical series, you have to remember it, because this one, it will be needed when we will be doing the structures, hybridizations of the coordination compound on the basis of VBT theory. So this one you have to properly, you have to by heart it. Okay, got it? Now I hope you have understood. Let's move to the next topic. Okay, now we are going to study types of octahedral complexes. So there are two types of octahedral complexes. One is inner orbital complexes and one is outer orbital complexes. Okay, so inner orbital complexes are those these complexes, those complexes which are produced when d orbital of inner shell, that is n-1 d, Okay, if the electron is lost from here, that is the inner d orbital shells, if the electrons are lost from the inner shell, d orbital of inner shells are used in bonding, then okay, if the electrons lost for the formation of bond is from the inner d orbital, okay, then they are producing, they are going to produce what? Strong ligands, okay, and these are also called as what? Low spin complexes due to electrons pairing. And mostly you will find that the electrons will be paired up in this case, okay. In this case the electrons will be paired up, okay. In inner orbital complexes you will find that the ligands will be strong field ligands, and there will not be much empty orbitals. So most of the orbitals will be paired up, and electrons here it will be lost is from the inner d orbital cells. That's why the hybridization is dsp3, okay. Got it? Inner d orbital is losing the electron now, okay, so the hybridization will start this way, d2sp3. And outer d orbital complexes means if the complexes are in the outside, okay. Okay, like example I will tell you, 1s, 2s, 2p, 3d. Suppose 3d is there, this is p, so this is called as outer. If it is like this, 4p and then 4d. If the electrons are lost from here, this is called inner d orbital, okay. Inner d orbital, this one is the outer one. If they are losing it from outermost, then the outer d orbitals, okay, outer orbital complexes. Okay, so the second one we are going to discuss is outer orbital complexes. These are these complexes are produced when d orbital of the outer shells, that is nd, are used in hybridizations, okay. These are produced by a weak ligands. So these outer orbitals are weak ligands, okay. These are also called as high spin complexes due to greater number of unpaired electrons, okay. So these are called as what? High paired these are called as high spin complexes due to greater number of unpaired electrons. Study the application of VBT theory. This is application of, okay, applications of VBT theory, okay. Got it? VBT theory applications we are going to study, and this one is very important questions for your board exam. It comes for 2 to 3 marks every alternative years, okay. So dear students, you need to see properly and try to understand it. So here the complex given is CrNH3 6 times 3 positive, okay. Got it? So first of all, what we have to do, we should know the electronic configurations of the central metal atom. So the electronic configuration of central metal atom is Cr equal to, there are shortcut also, but let us go for a long cut. Okay, so we are writing the complete electronic configuration: 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, 3d5. As you know, chromium electronic configuration falls under exceptional case. That's why it is 4s1 or 3d5, because D cannot be half 4 or 5. It should be half filled or it should be full filled. Already we have studied this in class 11. So now we are going to find out the oxidation number of Cr. So oxidation number of CrBx, and ammonia, you know very well, it is a neutral compound. So oxidation number is 0. And here how many ammonia is there? 6. So 6 into oxidation number 0 equal to, what is the charge? Plus 3. So plus 3. So if you cancel it, the x equal to plus 3. So we got the oxidation number how much? Plus 3. So chromium in ground state. So chromium in ground state, see, we are not going to consider the whole electronic configuration, only the outermost one we are going to consider, the valence shell. Okay, so this one only we are going to consider. So outermost, what is the thing? 3d5 and 4s1. So 3d, how many electrons are there? 5. So 1, 2, 3, 4, 5 electrons. And in 4s, how much? 1. After 4s, it comes what? 4p. So we have written 4p here. Okay, we don't have the electrons in the 4p, so just keep it empty. In the next state, what we are going to write, oxidation number is 3. So we have written Cr3. That is this Roman 3, it indicates the oxidation number. That means Cr3 means this chromium has lost 3 electrons. We are getting positive means it has lost 3 electrons. So 1 2 3. Okay, 3 electrons is lost. Now how many will be left? 1 2 3 will be left, and these all boxes will be vacant. These all orbitals will be vacant. Okay, now in the next step what we are going to do, we are writing the same thing. Now we have to see here NH3 6 NH3 is there, means we need 6 vacant d orbitals in which ammonia is going to form a coordinate bond with the central metal atom. 6 bonds it will be forming, so 6 vacant space should be there. So let's check 1 2 3 4 5 6. 6 are there. If not there, then you have to add another next subshells, that is 4p 4d, you have to add it. Okay or not? But it is already available 6, so we are not going to extend it. So here we are dotting it and making it together, all the vacant spaces 1 2 3 4 5 6. So now we are going to write the hybridization. How to write the hybridizations? In 3D, how many vacant boxes are there? 2, so D2. S, how many vacant boxes are there? 1, so S1. And P, how many vacant boxes are there? 3, so D2 SP3, or you can write SP3 D2. Okay, got it or not? So this is the hybridizations. So one thing is done. Next, the formation of Cr NH36 positive. What we are doing in the next step, in all these empty boxes you have to write XX. That means both the electrons will be contributed by this one, nitrogens, to form a coordination bond. So it is forming nitrogen, NH3, 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 NH3. It has formed a coordination bonds. Now always remember, if there is any single lone pair electrons in an orbital, then the magnetic behavior will be paramagnetic. If all is paired up, then it will be diamagnetic. But here you can see all these 3 are lone pair or not. So the complex has paramagnetic nature. Why? Because it has 3 lone pair of electrons. And what will be the geometry, that is the structure of this complex? So already I have given you the table. You have already seen that D2sp3 structure geometry is what? Octahedral. So this is the questions. Only for doing this much, dear students, you are going to get a good marks, that is 2 to 3 marks. So you should learn it properly. Okay, there are 4-5 questions are there, we will be doing it. Okay, let's do the second questions. Second question is CONH3 6 and 3 positive ions. Okay, so here the electronic configuration of cobalt, this is cobalt, so cobalt oxidation electronic configuration will be writing, it is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2 and 3d7. So those of you which you don't know, those of you who don't know the electronic configurations, again I will tell you that you should learn it properly, because it is very 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 important. Okay, got it or not? Okay, now next, after electronic configuration, our work is to find out the oxidation number. So oxidation number will be how much? It will be 3 only. Why? Because cobalt will shoot it as X, and ammonia ka oxidation number is 0, 6 is there, and charge is +3, so X will be equal to +3. So oxidation number is +3. Now we have written cobalt in ground state. So electronic configuration of cobalt in ground state. So when you write the electronic configuration of cobalt in the ground state, what will happen? See here, it is how many? 3d7. So 1 2 3 4. First of all, you have to fill it singly. Okay, this one already I taught to you in class 11. So 1 2 3 4 5 7 is this. So now you will start filling. So 6 7. 4 is how much? 2, and 4p is still vacant. There is no 4p orbital here. Now cobalt in +3 oxidation state. This is 3 oxidation state. That means cobalt is going to lose 3 electrons. We have lost it. So when we lost the 3 electrons, always remember the electrons first will be lost from the outermost, then it will come inward. Okay, so outermost is 4s. So from 4s we will be losing 2 electrons, and it is 3. So one more it will be lost. So that one will be lost from here. So here now the electrons left is 6 electrons are left in 3d. Okay, and 4s there is nil electrons. Now cobalt 3 oxidation state in this is in the ground state. Now excited state. In the excited state, you will see that the previous question there was no excited state. Okay, it depends upon the it depends upon this what we call central metal atoms. Okay, so here you will see that this O electrons and this electrons, it will come in the excited state and it will get paired up here. So when it gets paired up, these two boxes are empty or not. So we have to see that we should have 6 empty orbitals. So now you see 1, 2, 3, 4, 5, 6. 6 empty orbitals we have. So we will pair it up, and what will be the name? How many d orbitals we have? 2. How many s orbital? 1. p orbital? 3. So d2sp3. Now formation of this compound. So this one, it is paired up, and now the empty orbital will write Fs. That means their ammonia will be coming for donating the electrons to form the paired electrons. Okay now. Then what will be the nature of magnetic behavior? Will be what? Magnetic behavior will be dimagnetic, because all are paired up. So dimagnetic. If even one single is there, which is one pair, then it will be para. But here there is no single, all are paired up. So we will write the complex has dimagnetic nature. And what is the hybridization? D2sp3. So you can see in the table I have given you in the earlier of this class, in the first part of this class. So you can see the table D2sp3. If hybridization is there, what is the geometry? It is octahedral geometry. Okay, I hope you are understanding it. It's very simple. All of you try to learn it properly. Okay, let's go to the next question now. We take it down. This is all octahedral geometry, the questions we are doing now. Then we will go for tetrahedrals and square planar geometry. Okay, that means coordination number here. All 3 we have done. In that 3 also we have seen that it is 6. So coordination number is 6. So we are doing only those complexes which are coordination number 6 first. Then we will go for the coordination number 4. Okay. So again here you see FeH2O6. So the electronic configuration, it is what we are going to consider only this electronic configuration. As I will remind you again, this is the outermost, so we are going to consider this one only. Okay. So Fe in the ground state we have written it in the 3D. How many electrons? 6. 1, 2, 3, 4, 5, and then double it. So 6. And 4s, how many electrons are there? 2. So 2 electrons. P, is there any P? No. So done. Now we have to find out the electronic oxidation number. So 6 into x plus 6. 6 is water molecules are there. So 6, and water is in neutral. So 0 is equal to plus 3. Power is plus 3. So x equal to plus 3 oxidation state. Some cases it will be minus also. So that one you have to take care of it. Okay. Now Fe3, oxidation number is 3. So 3 electrons we are going to remove it. 2 electrons from here, 1 electron from here. So 1, 2, 3 electrons we have removed it. So now all will be singly clear. And what is left out? These are the left out ones. So 1, 2, 3, 4. Only 2 is left out. 4 is left out. But we need how many? 6 orbitals, vacant orbitals we need it. So here we have to add 4d also. So from 4d we are going to take 2 vacant orbitals. Now remember, dear students, since we are taking d orbitals, we are utilizing d orbital from the outermost. So it is called as outer orbital complex, or it is called as high spin complex. As a result, there will be no excited state here. Okay, no excited state will be taking place here. Remember that. Okay. Again, I am telling you here there is no contribution in hybridization of the inner orbital. We are taking a contribution from the outer orbital, that is 4d. That is why this complex will be called as what? Outer orbital complex or high spin complex. Okay, if we say if this 3d is contributing in the hybridization, then we call it as inner orbital complex or low spin complex. Okay, in low spin complex you will find that there will be excited state also will be there, but here you don't find any excited state. Okay. So this one, if you combine it, how many s orbital? 1, p orbital 3, and d orbital 2. So hybridization is sp3 d2. Now formation of FeH2O6. So this one too, it will remain as it is, and here these 6 boxes which we have grouped it together, there 2 x will be drawing, and then we will write downside water. That means what? Here water is going to form a coordinate bond with the central metal atom. So the complex has, see, all are one pair on, so paramagnetic nature and octahedral geometry. Why octahedral geometry? It is having, because I have given you the list. If the hybridization is sp3d2, the structure will be octahedral, and it is a high spin complex or outer orbital complex. Why? Because outer d orbital is participating in the hybridization, not the inner one. That is why. Okay, so I am going to give you related to octahedral structure 4 questions. All of you will try at home. If you find difficulties, feel free to ask your doubts. Okay, so homework questions I will be giving you. First you take down this one. Hope you have taken down. Okay, so homework questions, all of you will note it down and then you will be doing it and showing to me. Okay, these questions from this chapter, everyone, again I'm telling you, very important it is. So homework questions, homework number 1. Okay, number 1, COF6, 3 negative. Number 2, Fe, CN6, FeCN6, 3 negative. Okay, and then next FeCN6, 4 positive. Okay. Okay students, so we are back with the question number 4, and here we have our earlier coordination number was 6, here the coordination number is 4. This is second type. Okay, so in this coordination number 4, almost all you will find that they will undergo excited state. Okay, so here we are writing the electronic configuration of Ni is equal to 1s2, 2s2, 2p6, 3s2, 3p6, 4s2 and 3d8. So here we are going to consider only the outermost one, that is this one we are going to consider it. Okay, others we are not going to consider. So the nickel in ground state we have written here this one in 3d, 8 electrons and 4s2, 4p is there. After that what we have to do, we have to calculate the oxidation number of nickel. So oxidation number of nickel here will be x plus 4. Nickels are there and Cn oxidation number is -1, so -1 equal to -2 because power is -2. So x minus 4 equal to -2. This 4 if you take that side, then -2 plus 4 it will become +2. Okay, now Ni2, that is oxidation state, that means 2 electron has to be lost, and as I have been telling you that 2 electrons will be lost from the outermost. So outermost is 4s, so from here 2 electrons will be lost. Okay, so we have 1, 2, 3, 4 vacant orbitals already we have. Okay, fine, but Ni in excited state, this Ni2 it will go excited state, so this one it will pair up with this, the last one will come and pair up with this one will be pairing up. Okay, this one it will come and pair up with this, so this orbital will be vacant. So here the hybridizations will be, the contribution of 3d is 1, so ds is 1. Okay, 1, p is how much? 2, so dsp2 or sp2d hybridizations. Okay, so dsp2 hybridization. So formation of this, the remaining 4 boxes will be filled with the Cn. Okay, that is nothing but they are forming a coordination bond with nickel. Now as you can see, all are paired up, so the complex will have dimagnetic nature because all are paired up, no lone pair. So dimagnetic nature, and geometry will be dsp2 geometry. Already I have given you in the table, it is what? Square planar geometry. Okay, so similarly dear students, all are almost 90% same only. I am giving you 3 questions which you need to do at home, try at home. Okay, so first you take down this one. I hope done. Okay, so the homework questions here, it will be see, sometimes you need to give the homework also, because last few videos lecture I have seen that all of you are just simply you are watching the videos, you are copying down the notes, but you are not studying at home. So this homework will help you. Okay, so homework questions number 1. Okay, NiCl4 2 negative, NiCl4 Cl4 2 negative. Number 2 NiCO4 NiCO4. Okay, then next one is NiCO5 NiCO5. This is of here the coordination number is 5, so all of you will try this one. Okay, now let us move to the last topic of this chapter. Okay, questions was asked this year, got it? So this is important topic. 2 marks questions was asked in NBSC. Okay, got it? In 2020, 2 marks in NBSC 2020. These questions from this section, 1 questions came. Okay, so you have to understand it properly. Crystal field theory. So what is crystal field theory? Let us what is the crystal field splitting and all those things, what basically it means, let us try to understand. So all the 5d orbitals, as we know, in the d there are how many orbitals? 5 boxes are there. These boxes are nothing but orbital. All the 5d orbital have equal energy. These 5d orbitals, they have equal energy. In class 11 already I taught you the shape and the name of all the 5d orbitals, right? It was dxy, dyz and dxz, dx square, y square, dz square, right? So the shapes already we have taught you in class 11. So now I am not going to discuss about the shapes. Let us try to recall our class 11 things. All the 5d orbitals have equal energy. These 5 orbitals are there, or these are d orbitals. They have equal energy. So those orbitals which have same energy or equal energy, we call it as what? Degenerated d orbitals. So all the 5d orbital have equal energy, so they are degenerated d orbitals. Okay, no? So they are called as what? Degenerated d orbital. Okay, full stop. But during bond formations, like when the bonds are formed, these during the bond formations, these 5 degenerate d orbital splits. Now when the bond formations will take place, what will happen? These 5 d orbitals of same energy, they will split into 2. Okay, they will split into set of 2 unequal energy. So this is 5 together. Okay, so these 5 together, they have same energy, but during bond formations they will split into 2 orbitals, 2 different sets, okay, of different energy. So in the first set you will see upper side you have written d square, dx square dash y square and dz square. These are of higher energy level, will be on the upper side, and the orbital of lower energy level will be on the bottom side. So into 2 sets of unequal energy, this splitting process, we call it as what? Crystal field splitting. Got it? Okay, now we have taken one example of octahedral complexes. If octahedral complex is there, how will be the splitting of octahedral complex? Okay, so in octahedral complex, so this is the d orbitals. We have degenerate d orbital in the ground state, means they have the same energy. All the orbitals, they have same energy and they are in the ground state. Okay, got it or not? So in the normal state, that means ground means we can say normal state. Okay, so they have the same energy and they are in degenerate d orbitals. Okay, now what will happen? They will split into 2 different sets. One set we call it as pg orbital, another set we call it as t2g orbital. This, the downside, the lower energy, the downside is having lower energy, upside is having higher energy orbitals. Okay, so lower energy orbital we call it as what? 2t, t2g orbitals, and upper orbitals, that is higher energy, we call it as pg orbitals. Okay, so the energy of splitting, this delta naught is there, that is called as a splitting energy. So the splitting energy here on the upper part is 0.6. okay, splitting energy, and in the lower part, as I told you, the energy will be low. So it is minus 0.4 d del naught, that is splitting energy. Okay or not? Got it? So the difference del naught, this splitting energy, del naught is called as splitting energy, and P is nothing but pairing energy. Pairing energy is valid here and splitting energy is valid here at these sections. Okay, now let's see two conditions. If pairing energy, okay, P is smaller than splitting energy, if the energy required to pair up all these 5 orbitals is less than the energy required to pair up, then the pairing occurs. Okay, so if the pairing energy is less than the splitting energy, in that case pairing will occur, they will pair up. Okay, and then that case we call it as what? Low spin. Okay, if pairing energy is greater than splitting energy, in that case splitting will occur, and that is called as what? High spin. Okay, I hope all of you have understood it. Now let us go to the next sections. Okay. Okay, so the second type of crystal field theory is crystal field splitting in tetrahedral. The first one we did it for octahedral, this is for tetrahedral. Okay, so this is our degenerated d orbitals, that means of same energy level. Now here we have splitted it. Here the orbitals names are different. Okay, as I told you, the upper side it will be higher energy level, and in the lower side it will be lower energy level. So in tetrahedral geometry, these two parts, in octahedral you see this one it was having a higher energy level, so it was up. But in tetrahedral geometry, this dx square, y square, and z square, these two orbitals they will have lower energy level, whereas the first 3 orbitals they will have higher energy level. So we have written it on the top. Okay, and that orbitals we call it as what? T2 orbitals. Okay, this one is only for tetrahedral, and the downside we have a set of orbitals, that one we call it as E orbital, that is dx square, y square, dz square. Okay, so the center line which separated, this is called as barycenters. Okay, and the energy levels, okay, del T means what? That is nothing but this del T, it is nothing but energy level in tetrahedral. Okay, splitting energy in tetrahedral, there we have used del naught. In octahedral we have used this one, del naught, right? That is splitting energy in octahedral. This is splitting energy in tetrahedral. Okay, so upper portions the energy is what? 0.5 del T, that means splitting energy in tetrahedral, and in the lower portions we have energy how much? 0.6 del T, that means minus 0.6 del T. Okay, that means splitting energy in tetrahedral. So this energy gap we call it as what? Splitting energy. Okay, so this one we have done. Now let us see the crystal field stabilization energy of tetrahedral complexes is less than octahedral complexes. Means what? The crystal field stabilization energy in tetrahedral, it will be less than octahedral. Okay, so why it is so? What is the reasons? Let us see the reasons. Reason number 1, in tetrahedral complexes there are 4 ligands. Okay, definitely in tetrahedral complexes there are 4 ligands. We have already seen there are 4 ligands here, CO, CN4. So here how many ligands are there? 4 ligands. Okay, instead of 6 ligands in octahedral. In octahedral you will find that it will be like this, CO, CN 6 times. So here complexes is ligands is 4, here ligands is in tetrahedral ligands is 4, octahedral ligands is 6. This decreases the value. Okay, so because of this the value it will decrease. The value of what? Del splitting energy value will decrease. So 4 by 6, tetrahedral 4, octahedral 6. So 4 by 6 it will come how much? 2 by 3. That is the number 1 reason. Number 2 reason, in tetrahedral complexes ligands are not exactly in XYZ directions. So in tetrahedral you will see that the ligands will not be directly it will not be exactly in the directions of x-axis, y-axis and z-axis. Okay, but in octahedral the directions of the ligands are exactly in x, y and z directions. Okay or not? So this decreases the value further. So because of this, in octahedrals you will see that they are directional. They have x-axis, y-axis and z directions, they are available. But in tetrahedral they are not exactly in x, y and z directions, because of which the energy of splitting or energy of stabilizations decreases further. So 2 by 3 del t. So here del t it will be equal to what? Square of it. So 4 by 9 of tetrahedral energy of split. Okay, tetrahedral energy of split will be equal to 4 by 9 times energy of split of octahedral. So this is the end of this chapter, students. Hope you have understood it. Watch the videos properly again and again if you are not understanding it. Okay, and don't forget, if you are new to the channel, don't forget to like and subscribe the channel. Hope all of you have understood this chapter. If you have any doubt, feel free to ask your doubt. Okay, next chapter which we are going to start is organic. We are going to start chapter number 10. All of you keep watching, keep learning.